Okay, assalamualaikum and very good night basically. Uh, okay, so today we will continue with our next lecture, which is lecture number 8. Okay, so so on the lecture number 8 is about a dynamic vibration absorber. Okay, which later you will also assign with the group projects one. Okay, actually I've already put the instruction at the e-learning website so that you can go there and download and go through first what the project is all about. Okay, it's more on the actually the from the experimental method and how you can think to make it as a report that only have a calculation and also some discussion about the output of the experimental result, even though you are not doing the experiment, but there's something that you can think about and then you can do the report lah. Okay, so okay, so today is about the dynamic vibration absorber. Okay, so so basically when we have to consider that a harmonic disturbance to a single degree of freedom system. Okay, so basically for this topic is about a single degree of freedom. Okay, that we add on the dynamic vibration absorber system, and then the system will become the 2 degree of freedom. Okay, so actually the added degree of freedom is actually to reduce the vibration of the single degree of freedom system. Okay, it's mostly like similar to the previous lecture on the force 2 degree of freedom system. Okay, but the another degree of freedom is to reduce the vibration of the another degree of freedom, the primary system. Okay, so suppose that the disturbance will cause the large amplitude of vibration, okay, of the mass in the steady state lah. Okay, we always consider of steady state condition. So a vibration absorber is a uh, secondary spring mass system that added to the primary system lah. This is our first degree of freedom system, and this is our second degree of freedom system that designed to absorb the input disturbance by shifting the motion to the new added mass. Means that all the vibration for the primary system uh, is shifted to the DVA mass. Okay, so that the basically in theoretical the primary system vibration will become 0, and then the all the vibration will transfer to the DVA lah. Okay, and that's what we call the absorber mass. Okay, so this is considered that we have the a typical this force vibration single degree of freedom system. Okay, where we have a stiffness. Actually this you can write as 1k actually. Okay, this is k over 2, so the total in the parallel is equal to k. Okay, this is the mass. Okay, and the force, okay, the excitation force, okay, f naught sine omega t, and there's a response of xt. Okay, so suppose the disturbance will cause the large amplitude variation in the mass of the mass in the steady state. So sometimes it become a resonance also. Okay, before that, we see the example of how the DVA can contribute to the reduction of the vibration. Okay, in this situation where there's a bridge. Okay, and then there are person there that will jump on this bridge and they will cause a resonance. Okay, and then when the DVA is reduced, the vibration will be stabilized. You can see that when they jump into the bridge, it's caused a high vibration. Okay, so at the time of 0.44 seconds, okay, somewhere here, okay, the DVA will be installed, and then you can see that all the vibration is transferred to the DVA system, and the vibration of the bridge becomes stable. Okay, so what you can see here, this is the DVA system. Okay, even though they are excitation force at the bridge, there's no vibration, okay, at the bridge, okay, and the vibration is actually transferred to this the mass of the DVA, okay. Okay, so it's like the experimental is successful for them, okay. Okay, so a vibration absorber or DVA is a secondary spring mass system that added to this primary mass. Okay, we have the primary mass, the primary system. Let's say there's the bridge is designed as a single degree of freedom system. Okay, and there's the force excited by the pupil there. Okay, then the vibration of the bridge is high. Okay, so it's designed to absorb the input disturbance by shifting the motion of to the new added mass called the absorber mass. So all the vibration as the primary system is transferred to this DVA. So this vibration, the X will become, the XT becomes 0, and then the XA will become large, but it's basically it doesn't affect to the primary system because there's another attached system mass that will be vibrate. So this is the same what you have learned before, okay. Okay, DVA concept when the primary system experience resonance, the thing that you have shown in the video before. So the added absorber system as indicate, okay. So the added system of the, okay, of the MA and KA, okay. This is the DVA, and look at the equation of motion of the system. Okay, now it's become 2 degree of freedom system. So basically this is similar to the equation of motion of the 2 degree force vibration. Okay, just imagine that the M2, K2 and X2 become MA, KA and XA, but what you have to alert, this is the VA, is not the what we mean the primary system that will have the secondary system that will excite the vibration, but this one will basically absorb the vibration. Okay, so basically we can, as usual, okay, maybe I can write down here. Okay, we have a, okay, so we have a mass. So, okay, so we have the MA, okay, KA, the M, okay, and the K, okay. So this is the primary and this is the DVA, okay. So there's the XT, okay, by the primary, and there's also the XAT by the DVA, okay. So the force is here, okay, okay, where actually is equal to F naught sine omega t, okay. So as usual, what we can do here, okay, we can derive the equation where, okay, when you can draw here, divide by 2, so there will be upper side of plus and below side as minus, okay, also the same is plus and minus, okay. So what we have here, okay, so for the upper part there is no connection here, so it becomes 0, okay, and for the MA, the below parts, okay, is minus, okay, minus KA, okay, and then it's XA minus by X, okay, and for the plus part, okay, for the below part, this is the connection, there's the connection here, At the plus part, okay, is have a k. This is the k x a, okay, minus x, okay, the same one, and the below part is k minus k x, okay. So of course for the MA is a total of MA XA double dots, and for the primary part is MX double dot, okay. So from this, okay, we can write down the equation of motion, okay, for the MA, okay. The total force is minus KA, okay, XA minus X equal to MA XA double dot, okay. And for the M is total force, okay, we have F here, okay, F naught sine omega t, okay, plus direction, okay, and also the plus direction is plus K XA minus X and minus KX equal to MX double dot, okay. So by rearrange these two equation, okay, the same one when you arrange by the acceleration, velocity and displacement, okay, and also by M and after the MA, so basically you will get this, okay, this equation of motion in term of metric form, okay. So you have MA, okay, the acceleration x double dot SA double dot, okay, this is the stiffness, okay, the displacement, okay, and also the force, okay. Okay, so what we can do from this, okay, okay, to solve, we assume that we have the harmonic displacement excitation, okay. We have given the F naught sine omega t, so that your trial function must be in terms of sine, okay. The xt is x bigger x sine omega t, and xa is xa sine omega t, okay. So by rearrange and simplify, it's become like this, okay. Okay, it's always the same, okay, what you have done before, okay, for the 2 degree of freedom force vibration, where we have the similar of the symmetric, okay. Okay, when you refer back to equation 50 in the 2 degree of freedom of free or force vibration, the two elements here is actually replaced by a element because of the DVA, okay. So the same technique, when you move to the right hand side, okay, you can replace as the impedance matrix. You move to the right hand side, it's become inverse, okay, and you can solve the equation similar as a force variation, where you can determine the x and xa, okay. Okay, so this is the most important part I want to highlight. Okay, the solution response method will become in terms of these two, okay. This is the basically the amplitude of the primary system, and basically this is the xa is the amplitude of the what we call it, the DVA, okay. So you can have the total equation like this, okay, for the x and xa. So how you want to make the primary system become zero, okay. So pick, okay, we must basically design, okay. Now we have the excitation frequency from the force, okay. Let's say you have the motor to the system, and the motor is running at like 200 rpm, okay, or maybe 200 hertz, so that actually you can design the DVA, okay, to match the operating frequency. Means that we have the omega actually, okay, okay. So basically in this, okay, we already know that omega, okay, So maybe we can have actually omega equal to k over m, right? Okay, so we can design that the DVA have the omega a equal to ka over ma. Okay, okay, so by omega a2 is actually ka divided by ma. Okay, so by this actually, when you can see here, okay, when we design, okay, the DVA, the DVA natural frequency is the same as the operating frequency. So okay, where omega a is the same as the operating frequency, okay, you can replace ka over ma here. You can slash out the ma, and ka will minus by ka, so it will become 0, so that the primary system vibration is become 0, and everything is transferred to this amplitude, okay, of the DVA. Okay, by pick ma and ka to make it as a 0. Okay, so all the system motion goes to the absorber motion. Okay, this is what you have to know about the system. Okay, okay, so we choose the absorber of the mass and stiffness from this, okay, where omega 2 is equal to ka over ma. Okay, this cause the primary mass to be fixed, okay, and the absorber mass to escalate at this lah. Okay, so basically when you have the system of this, okay, okay, so when you have the system of this, actually the x will become 0. Okay, the xa will become like this. Okay, this is the amplitude of xa sine omega t. Okay, okay, when you solve it, okay, this one will have a amplitude like this lah. And then when you replace to the xa equation, okay, it's become the displacement like this. Okay, so this is the actually the okay, so we can continue here. Okay, as in this case of isolator, the static deflection, which means that the amplitude of the absorber, okay, will become static deflection is a rattle space, and also the force magnitude need to be checked in each design lah. So it's actually need a specific design to make your absorber is become effective. Okay, okay, so this is some of the disadvantage of the DVA. Okay, it actually depends on the knowing omega. Actually, you must have to know what is your operating frequency, so that you can design your DVA. Okay, the natural frequency of DVA can be made of as a what is the operating frequency is. Okay, so it must be a single frequency device. Okay, so that because the DVA can only meet to the one operating frequency, so that you have a very specific lah. I mean that you cannot counter system that have two operating frequency using a one DVA. You must have two DVA to counter for each of the operating frequency. Okay, so if the omega, okay, if the net operating frequency shifted, it could be end up by exciting the system lah at the natural frequency. Okay, because by applying the DVA, actually the natural frequency of the primary will shifted, and it become the addition of two natural frequency, but it's a more smaller amplitude. Okay, but later I can show you how this effect. Okay, so the damping which always exists in some of degree can spoil the absorption. Okay, so when you add some damping to the DVA, means that DVA will lose its function. Okay, okay, so this is some of the equation, the simple parameters that you have to know. Okay, in terms of mu is the mass ratio, the mass of the DVA divided the mass of the system. Okay, the natural frequency of the primary system. Okay, for this we have omega. This period omega is the operating frequency. It means that if you have a system and then you have a motor attached to it, and the motor operate, That's the omega, the operating frequency. But omega p is actually the natural frequency of the your primary system. Okay, like the bridge system that I showed you before. Okay, the bridge have the natural frequency of omega p. Okay, when there's the pupil jump on it, okay, they will create the excitation frequency, which is omega. Okay, so please be alert. Okay, and then omega A is the natural frequency of the DVA that you design to equal to omega. Okay, you design the DVA. Okay, the omega A is actually equal to the omega that, example for the bridge system, you design the omega A of the DVA to become the same as a omega, the excitation from the pupil. Okay, so actually this is a more simplified form. Okay, in terms of stiffness ratio, Ka divided by K. Okay, when you use the equation omega equal 2 pi f. Okay, sorry, when you use this equation omega equal to K over M, actually you can have this more simplified, and it will become omega beta the power of 2. Okay, okay, so actually the beta is a omega A divided by omega P. Okay, okay, and we have also the frequency ratio of Ra, okay, which is omega divided by omega A, and Rp is omega divided by omega P. Okay, Ra is omega, which means the operating frequency divided by the natural frequency of the DVA, and Rp is omega, the operating frequency divided by the natural frequency of the primary system. Okay, okay, so this is when you have the, okay, this is the thing that you have learned. Okay, the four equation that you have to know and understand. You don't need to remember it because it will be given in the final exam or test. Okay, because it's complicated equation and it will be given, but you have to understand it. What is the function of this equation? Okay, so equation 53 and equation 54, when we replace with all these parameters, so it will become this condition lah. Okay, in terms of equation number 55 and 56. Okay, from equation 53 and 54 can be rewritten as this. Okay, okay, omega divided by omega A is actually the Ra, omega divided by omega P is actually Rp power of 2. Okay, and so on. Okay, this is the Ka divided by K is mu B, the power of 2, the similar as what I have write down before here. Okay, so of course you need to know, okay, each parameter is stand for what, but it's not necessary for you to remember it lah. Okay, okay, so from this this is actually what will happen to the system when you add on the DVA. Okay, so basically you will have a one peak here, okay, of the operating frequency, sorry, okay, the operating frequency of the system. Okay, when you add on DVA, okay, it will reduce totally to get a zero vibration here, but it will induce another too small of natural frequency for the system. Okay, so that's you need to operate. Let's say you have an operating frequency of 200 hertz, for example. Okay, you already designed where omega divided by omega A is equal to 1, which means that operating frequency of the bridge, okay, for example, you have 200 hertz, and then omega A, you have a 200 hertz, you design as similar as an operating frequency, so that you get 1, okay, frequency ratio. Mean that at that location, you become zero vibration of X, okay, the amplitude of the primary system. But it will induce two natural frequency here, so that you can still I mean, there's some allowable frequency range for the different frequency. For example, let's say suddenly there's some effect, external effect, the operating frequency of the brick is slightly shifted. Okay, if the frequency is shifted, it must be in this range. Okay, so in this range, so that if it above this range, it will induce, okay, it will go to the new induced natural frequency, so that it will the system become resonant again. Okay, that's the thing that you have to alert. Okay, so this is omega divided by omega 1, omega divided by omega 2. Omega 1 to omega 2 is the new frequency range. Okay, we call it absorber. Okay, the absorber zone. Okay, if we eliminate the amplitude of the operating frequency, is induced to natural frequency omega 1, omega 2. then operating frequency must be avoid this 2. It must be in this absorber zone. Okay, maybe I can draw it for you to become more understand for this. Okay, let's say, okay, you have we can okay, maybe we can clear this. Okay, so let's say this is your system. Okay, you have this. Okay, you have this. Okay, this is omega. Okay, let's say you have an operating frequency of 200 hertz. Okay, for example. Okay, and then when you apply the DVA, okay, actually it will become like this. Okay, so this is omega 1 and omega 2. Okay, we induce two new natural frequency, but what you can see here is become 0. Okay, where omega equal to omega A. Okay, where we design the natural frequency of the DVA is equal to operating frequency, so the vibration will become 0, and it have lower the new range of operating frequency. Okay, so let's say you have we assume that the new range is about 180 hertz, or this will become 220 hertz. Any shift of the operating frequency when you already design the DVA to become equal to 200 hertz, means that you must maintain the operating frequency of the system. When the operating frequency is shifted, you must confirm that this frequency range did not exceed 180 or 220 hertz, unless it will induce at the new induced natural frequency on omega 1 and omega 2, and it will become resonance again. That's the thing that you have to alert. So this is in terms of amplitude. Actually the rule of thumb, the amplitude must be 1 or below. This is the frequency ratio lah. The frequency ratio. So from that, so this is what will happen lah. So you already designed your natural frequency, the operating frequency is equal to the DVA natural frequency, omega equal to omega A. So you see that the primary system in the blue color is become 0. There is no vibration. And the vibration is all transferred to the DVA system, the red one. So you must know this is the range of the allowable frequency range change. When it goes to the omega 1, you can see that it's excite at the new natural frequency of the system, and it will become high vibration again. So same again to this one, the upper range, the below range, and the upper range. When it's reach the omega 2, so it will become resonant again. So this is the range of the effective DVA. So if omega hits omega 1 or omega 2, the resonant occur again. That's the same thing that I have shown you before in the animations. By using this formulation, xk divided by f naught below than 1, this is actually the amplitude where you have the xk divided by f naught, below than 1. So it's defined the useful of operating frequency range for the absorber. In the range, the sum absorption is still occur. Even though there's a different in terms of frequency range, frequency excitation. So the absorption is still occur at this range. So this is the characteristic equation Okay, this is a complicated one, but this just to show in terms of characteristic equation, you need to know detail about it, but this is just to show you what it's all about. Okay, those for the frequency is depend on the mass ratio. Okay, these two parameters and also the frequency ratio. Okay, you must always alert these two parameters, the mu, okay, and also the frequency ratio. Okay, the okay, the difference of mass, okay, mean that the ratio of DVA mass and also primary mass, okay, and also the frequency ratio that determine the frequency ratio. Okay, okay, omega 1 and omega 2 here. Okay, okay, so actually this is omega E1, this one, omega E1, the effective range one, and omega E2. Okay, okay, the omega 1 and omega 2 actually the new natural frequency, but the effective range is until this value. Okay, okay, so this is the same thing. Okay, the DVA, the effect of changes of the secondary mass. Okay, referring to this figure 5.16, as mu increase, okay, as mu increase, we have this curve. Actually, this curve is actually this one. Okay, this curve, okay, is similar to this one. Okay, okay, so as mu is increased, frequency split further apart for the fixed b. Okay, we have a b mu, sorry, beta of 1. If mu is too small, okay, you can see here, mu is too small. Okay, if mu is too small, the system will not tolerate much in driving frequency, which indicate a poor design. Okay, you have, if your mass ratio is too small, it will become at this area. Okay, so it will not effective. Okay, but so the rule of thumb, we have must design our mass ratio mu to in this range, which is from 0.05 from here until 0.25. Okay, so the mass ratio mu, okay, it must be designed from 0.05, okay, up to 0.25. So this is the rule of thumb to make your DVA effective, so that when you want to design your DVA, the MA must be designed, you know your primary mass, right? Then and then you want to design the MA, it must be in this range basically. Okay, okay, so the next thing is about this. Okay, the dynamic variation observer. Okay, the effect of DVA to the primary system. Okay, firstly, okay, let's say you have this one, the blue one. Okay, down vibration absorber. Okay, the same one as what I had drawn, the black one here. Okay, which the vibration absorber, it become green one like this. So the same one is become the red one like this. Okay, so this is the effective frequency range. Okay, okay, the same one, the omega E1 and omega E2. Okay, so adding the absorber will increase the number of resonance almost from 1 to 2. Okay, this is the primary system. Okay, when you add the DVA, it will become 0, but it will add another 2 natural frequency. Okay, omega 1 and omega 2. But the good thing is the vibration at the operating frequency will become 0. Okay, smaller response of the primary structure is at absorbed natural frequency. Okay, so the smaller response of the primary structure is at the absorbed natural frequency, which means that the vibration will become 0, the small here. Okay, mean that the primary structure omega equal to omega A here at 200 Hz, for example, here it will become small. Okay, the effective over limited bandwidth, that's the bandwidth that I have said before, is only limited, and the design maybe is become in term of the range of 180 until to 220 Hz only. Okay, so this is the effective, the very limited basically. You cannot play around with your operating frequency very much. Okay, if there are changes of operating frequency, so it must be in term of this range. In the operational range of the vibration observer, the mass has relative large motion. Okay, of course, all the vibration of the primary system transfer to your DVA, so that your DVA excitation XA will become larger. Okay, so you have the X will become 0 and XA will become max. Okay, so this is basically what you have the effect of DVA to the system. Okay, so just beware of the deflection limits. Okay, of this bandwidth basically. Okay, so this is the example. Okay, how you can design your DVA. Okay, calculate the secondary mass. Okay, mean that you need to know your MA. What is your MA? And the bandwidth of the DVA. Okay, the omega E1 and omega E2. Okay, that needed for the system that operate at 800 RPM. Sorry, 180 RPM. Okay, so we have this value. Okay, the omega equal to 180 RPM. Okay, this is RPM. You must convert to radian per second. Okay, and then the F naught. Okay, equal to 30 Newton. Okay, this is the F naught. Okay, the mass of the primary system is 73.16 kg. Okay, the K, okay, the primary stiffness 2600 Newton per meter, and the deflection of DVA should be below. Okay, the XA must be maximum of 0.002 meter. Okay, so this is all the parameters that you have. Okay, so that how you can calculate. Okay, so based on previous equations. Okay, previous equation. Okay, so here. Okay, so XA, you have the XA here 0.002. The F naught is given. Okay, here, and now you can calculate the KA. Okay, okay, so you are already given the maximum deflection of XA, the F naught. Okay, the amplitude of excitation force, and now you can calculate the KA. Okay, so now you have the value of KA. Okay, this is K, and the KA is equal to 600 and 500 Newton per meter. Okay, so from that, okay, since you already have the you want to design. Okay, we always want to have omega equal to omega A. Okay, where you want to design your natural frequency of the DVA is equal to the operating frequency, so that using this one, KA over MA. Okay, you have the omega and KA. Now you can have the value of MA. Okay, using this equation, so that you can get the MA is equal to, okay, so your MA equal to 18.29 kg. Okay, you have already can get the MA. So now you have the MA and also the mass, so you can get the mu. Okay, then this is the stage when you can check your DVA is effective or not. So we have the effective frequency range of the mu must be from 0.05 up to 0.25. So now you get your value of 0.25, means that your system of DVA is effective. Okay, so next is on this calculation of DVA. Okay, for the frequency range, now we want to determine the omega E1 and omega E2 here. Okay, so as a rule of thumb, okay, it must be below than 1. The amplitude, the Xk over F naught must be below than 1. So we have this equation. Okay, refer back to equation 55 here. Okay, you have the equation of 55 here. Okay, by using this equation of 55, okay, actually the static deflection, okay, the f naught over k, okay, when you replace here, okay, this is the amplitude will become like this, x over k per f naught, okay, when you replace the static deflection here. Okay, so you can just replace it 1 and -1, okay, 1 and -1, so that you can find the roots. Okay, let's see the solution is a equation from 55. Okay, you already have the omega here, omega a, okay, you have the omega, okay, and omega a, okay, our omega a, okay, and then you have the mu, okay, you have the omega p, okay, where you can calculate from the mass and stiffness of the primary system, okay, and so on. Okay, actually you have all the parameters here, then you can solve it. Okay, so for the case number 2, you take one and another one is minus 1, okay, so that you can get another value. So from this actually you can get 3 value of omega. Okay, from that 3 value you can pick the lowest 2 value. Okay, means that you take value of 7.4 and 21 hertz. So this is basically the range of your effective frequency range, the omega E1 and omega E2. Okay, this is the range that the driving frequency can safely lie in, and the absorber will still reduce the vibration in this primary mass. So this is in this area. Okay, so the next slide shows you the detailed calculation. Okay, you can try to recalculate back, okay, one by one. So this is the thing that I showed before, the case number 1 when it equal to the amplitude equal to 1, and case number 2 when the amplitude is equal to -1. Okay, so you can calculate the natural frequency of the primary mass. Okay, you can get 5.69 radian per second, and omega a is the frequency that you already calculate before. Okay, you get 18.85 radian per second is equal to omega lah. Okay, which is the natural frequency of the DVA is same to the operating frequency of the system. Okay, when you go to insert all the values in this equation, you will get these two condition. Okay, get to the characteristic equation. Okay, replace with the a, b and c here, a1, b1, c1, and also a1, b2 and c2. Okay, this is a, b and c. There's no c here, but for this one they have c of 2 here. Okay, so from this, okay, basically you can get this 4 value basically, but this omega 1 is 0 because there's no c here. Okay, b minus b plus by b, so it becomes 0. So this you will get for this of this value 0, 21.12, 7.4 and 21.52. So for the to decide the range, you must take the lowest of 2 value, which is this is we cannot consider because it's 0. So you can get 7.4 until 21 hertz, 21 radian per second. So this is the same that shown before lah. You get 7.4 up to this 21 radian per second. So basically this is your effective frequency range. Okay, for the next one is what is the effect of damping to the system. Okay, let's say your system have the damping, you add the damping, the CA to the system. Okay, means that your DVA here, okay, let's say your system here, okay, you have the M, the primary, and then you have the MA here. Suddenly you add the damping CA to the system. Okay, okay, so what's effect to the equation? When you solve this equation, that equation 53, you can compare back with equation 53. Okay, this is equation 58. You can get this above side. Even though you want to design omega equal to omega A, only this part will become 0, but there's still a remaining of this part. Okay, so that's why when you add the damping, the primary peak will never become 0 because of the damping. Okay, when you add a damping to the DVA, so it will spoil the function of the DVA. Okay, it will cannot become 0. Okay, okay, so this we can see from this view. Okay, what is the defect of the damping? Okay, magnitude of the, we can give a three condition. Okay, where the first one, okay, the red one, okay, where this we consider the damping ratio of 0.01, which is very small, is almost zero damping. Okay, so it's still effective. Okay, we can get when the amplitude is 1 here. Okay, it must be below than 1 for the DVA to be effective. So this is basically the range. Okay, you can see the red one is the effect of DVA. It will become 0 here. When you slowly increase the damping, you can see the blue color. Okay, the amplitude will reduce here, but it's already going out to this range above than 1. Okay, and then when further increase to 0.4, it will going back to the original operating frequency. Okay, so let's say you have this amplitude of no DVA, and you added the damping, so it's just still remain at the operating frequency, but with a reduce of amplitude lah. But of course the function of DVA will be eliminated. Okay, as the damping increase, the absorber will fail, but the resonance will goes away lah. There's no resonance of these two, but the function of DVA will be spoiled. Okay, okay, the next one is on the more, is the same figure also. Okay, okay, where it is the same if the case of no vibration absorber. Okay, the thing that I shown you before, the blue one here. Okay, it's actually similar to this, the black one. Then you add the DVA. Okay, the green one. Okay, so with the amplitude of 1, okay, you still have this range of the effective operating frequency. Okay, and then you further increase to 0.1 and 1, so that's it will become red and it become blue, so it's already going above this range. Okay, and the amplitude of 1, so of course it will added the damping will spoil the DVA function. Okay, in the operating range of the, so the effect of damping, what is the effect of the damping to the performance of DVA? Okay, in the operating range of the vibration absorber, we decrease with the damping. Okay, and the function of the DVA will be reduced. Okay, the resonance are decreased. Okay, okay, there is no resonance of two resonance here. Okay, but it could be used to reduce the resonance problem. Okay, it can reduce the resonance of these two lah, but basically that's the effect of the damping, which means that it will decrease the operating range here. Okay, and also it will reduce the resonance, but going back to the original system with no vibration absorber, but with a reduced amplitude, but it will not become 0. If you have DVA, it will become 0, but if only damping, it will reduce but will not become 0. Okay, okay, so for this last slide, okay, this is some of the application of DVA. Okay, that also will be asked in your reports. Okay, so this is the helicopter. Okay, I already show you on the effect of rotating ambulance mass to the helicopter. Okay, it will become, the helicopter will become unstable. So what is the DVA can be one of the solution for that. Okay, and also this is the handle. Okay, when you have maybe you can put it on your bicycle handle or your motorcycle handle to reduce the vibration. Okay, so this is for the tower. Okay, where this basically installed in many of the famous tower in the world. They most of the tower have the DVA system. When there is an earthquake, the DVA will stabilize the vibration of the tower, okay, like the KLCC itself, okay, and also another the tower, famous tower in the world. Most of them have the DVA system to stabilize when there's an earthquake effect, excitation. And the last one is on the machine itself, where when the in the machine of the at the factory, when there is vibration from another machine, when you have the DVA, you can stabilize the vibration of the machine so that it should not affect your uh, fabrication works. Okay, that's the end of the DVA lectures. Okay, hopefully you can understand it. Okay, as usual, if there are any question, you can always ask me through the e-learning website. Okay, so enjoy your class. Okay, thank you very much.